When we have Lewis structures that have double bonds or triple bonds in them, we can often write more than one possible structure because we can put the double bonds or the triple bonds in different places in the molecule. This concept is called resonance, and let's look at, for instance, the carbonate anion. So the carbonate anion has a doubly bonded oxygen and two singly bonded oxygens. The singly bonded oxygens have 3 lone pairs, and the doubly bonded oxygen has 2 lone pairs. The whole thing is 2- charge. So I have written this structure with the double bond here, but there's no reason why I couldn't have put the double bond here or here. So a resonance structure is a structure where we keep the atoms in exactly the same place, but we move the electrons around. So for instance, if I take these 2 electrons and move them in here to make a double bond, if I did that, the carbon atom would have too many bonds. It would have 1, 2, 3, 4, 5. And so I need to get rid of one of these double bonds up here and take these 2 electrons and move them out so that my carbon atom doesn't have more than an octet. So if I do that, if I move those electrons around, don't change where the atoms are, just move the electrons around, I can redraw this structure, putting the electrons where I've now moved them. So now I've moved 2 electrons in where this oxygen was. I lost one of my lone pairs, and so let's make that one red so we can see which one we moved. I left this one alone. I didn't do anything to this one. And then I took one of these pairs of electrons and put them out as a lone pair on this oxygen. So those are the electrons that I moved. And when I did that, we can see that the double bond has now moved to be between this carbon and oxygen rather than between the top carbon and oxygen. So I've just moved that double bond around by moving the electrons. I can do that one more time. So let's do that one more time. Let's move these electrons in here and then move these electrons out here. And so now if I redraw this structure as I have moved the electrons, I will have not done anything to this oxygen, but I will have moved one of the lone pairs out to this, one of the bonds, the 2 electrons in that bond, out to be a lone pair on this oxygen, and I will have created a double bond between this carbon and this oxygen, leaving it now with only 2 lone pairs. And so you can see that there are 3 possible structures because there are 3 possible places where I can put that double bond. Notice that all that I've done is move the electrons around. So these arrows show where the electrons are moving, and that leaves the atoms exactly where they were. I haven't moved the atoms, all I've done is move the electrons. So resonance structures are structures where you've kept the atoms in the same place but moved the electrons around. When I can draw structures like these, where if I take one of these structures and I simply rotate this around like this, I will see that it looks exactly like this structure. Now the double bond is over here and the single bonds are top and to the left. So if I can just simply rotate the structure and get one of my other resonance structures, then in fact those are equivalent resonance structures. So let's rotate this guy back to where it was, and now we can say that An equivalent resonance structure is just a rotated structure relative to all the other structures. The other way to think about this is that I haven't changed the number of single bonds and double bonds between given types of atoms. And so those have stayed the same. They're equivalent. So you might well ask, why do we care about resonance structures? As it turns out, the more equivalent resonance structures that we can write, the more stable the atom, or sorry, the molecule will be. The reason for this is because when I can write equivalent resonance structures like this, it means that these two electrons in this that make up the second bond here, the double bond, these two electrons can be here, here, or here. And it doesn't mean that there are three different structures for this molecule. What it means is that these two electrons are delocalized between these three possible bonding spots. So these two electrons are now shared not just with this carbon and this oxygen, but with this carbon and all three oxygens. So now these two electrons can be attracted to 4 different nuclei rather than just 2, and that causes more attractive interactions, negative electrons, positive nuclei, attractive interactions. And the more the attractive interactions, the more we lower the energy of the structure. More stable means lower energy. So let's just write that out. So these equivalent resonance structures mean that the electrons that are moved are delocalized. That is, they are shared with all of the atoms that they can represent bonds between. So more nuclei electron interactions. So more delocalized means that those electrons are shared with more nuclei, so we have more nuclei electron interactions, implies more attractive interactions. And remember that attractive interactions lower the energy of the system. So attractive interactions lower the energy, and lower energy means more stable. So the more equivalent resonance structures, the more those electrons are delocalized or shared with more nuclei. That gives us more attractive energy, and more attractive energy means lower energy, and lower energy means more stable. Let's look at another example where there is resonance. So if we have the thiocyanate anion, SCN-, we can draw the following Lewis structure for this. So we have some double bonds here, which means that we can probably move some electrons around and make a resonance structure. So let's see what we might do. So we might move these 2 electrons in here and these 2 electrons out here. That would give us a extra lone pair on the sulfur and a single bond between the sulfur and the carbon. And it would give us an extra bond between the carbon and the nitrogen and 1 less lone pair on the nitrogen. So we could do that. Or we might move the lone pair from the sulfur in between the sulfur and the carbon, and an electron pair out onto the nitrogen. If we did that, we would end up with the structure where we have a triple bond between the sulfur and the carbon and a single bond between the carbon and the nitrogen, giving the nitrogen one extra lone pair and the sulfur one less lone pair. So we have three different resonance structures, but notice that these are not equivalent. They're not equivalent because there's not the same number of double bonds, single bonds, and in this case, triple bonds. So these are inequivalent resonance structures. Now, we might be able to distinguish which of these structures is the best, right? So which of these is the best Lewis structure? And the way we're going to do that is to use formal charges. So if we think about it, the atom that is the most electronegative is the one that's going to accept that electron more easily, is going to be lower in energy when it accepts that electron. So we would want the most electronegative atom to have any formal charge, any negative formal charges. So we want most electronegative atom to have any negative formal charges, and the least electronegative atom. So if we need to have some positive formal charges, then we want the least electronegative atom to have the positive formal charges. So how are we going to figure out which atom in each of these structures has a negative formal charge? Well, we're going to count up the number of electrons that each atom gets in the structure and compare that to the number of valence electrons each atom should have. So if we start over here, we can see that nitrogen has 1, 2, 3, 4, 5, 6, 7. One electron from the bond goes to the nitrogen. So this nitrogen has 7 electrons in this structure. And the carbon has 1, 2, 3, 4, one from each bond. So the carbon has 4 electrons in this structure. And the sulfur has 1, 2, 3, 4, 5. So in this structure, the sulfur has 5 electrons. So if we move into the middle structure, this sulfur has 1, 2, 3, 4, 5, 6 electrons. So this sulfur has 6 electrons in this structure. Carbon still has 4 electrons. And now nitrogen has 1 from each of the bonds, so 1, 2, and then 4 electrons that are lone pairs, so this nitrogen has 6 electrons in this structure. And then if we look at the one clear on the right, we can see that this nitrogen has 5 electrons, the carbon still has 4 electrons, and the sulfur in this case has 7 electrons. So how does that help us with formal charge? We're going to compare the number of electrons in the structure to the number of valence electrons for each of those atoms. So remember that nitrogen has 5 valence electrons, so it brought 5 electrons to the structure. Carbon has 4 valence electrons, it brought 4 electrons to the structure. And sulfur has 6 valence electrons, it brought 6 electrons to the structure. So if I then compare for each of these structures, let's look at the nitrogens first. The nitrogen has 7 in this structure. It should have 5, so it has 2 extra. So this has a -2 formal charge, the nitrogen. The carbon has 4 valence electrons, and it gets 4 electrons in this structure, so it's neutral. So in each case, the carbon stays the same, and the carbon is neutral in each case. The sulfur in the left hand, the structure on the left, has 5 valence electrons in the structure. It should have 6, so it has 1 less than it should have, and that gives it a formal charge of +1. So if I move into the middle structure, The sulfur has six electrons in this structure, and it has 6 valence electrons, so it has a neutral charge here. And then the nitrogen should have 5, but it has 6, so it has 1 extra. And then if I move to the one clear on the right, the nitrogen has the right number of electrons to equal the valence electrons, so it has a 0 charge, but the sulfur has an extra electron, so it has a negative charge. Okay, so let's just check and make sure that all of our formal charges add up to the charge on the ion. So notice that this ion has a -1 charge. So if I take -2 plus 1, I get -1. So I must have counted the electrons correctly. And then in the middle structure, if I take -1 plus 0, I get -1, so that's good. And then in the far right structure, 0 plus a -1 is also -1, and so it looks like I've counted my formal charges correctly. So now let's see if we can use our principle for which is the best structure. So the least electronegative atom is the carbon, and actually sulfur has about the same electronegativity as carbon does. So carbon and sulfur are the least electronegative atoms, and nitrogen is the most electronegative atom. So here nitrogen has the -2 charge, sulfur has a plus charge. So the least electronegative atom has a plus charge, the most electronegative atom has a minus charge. So maybe that's okay. In this structure, we've given the nitrogen a negative charge and the sulfur is 0 charge. So that makes sense. The nitrogen is the most electronegative. It has the negative charge. But over here, I've given the negative charge to one of the least electronegative atoms. And so I can probably pretty safely rule out this structure. So now if I'm looking at these two structures, how would I tell the difference? Well, the next thing that we have to think about is that in addition to giving the most electronegative atom the negative charge, we want to also minimize formal charges on all atoms. So if I look at this structure, 2 of the atoms have a charge and the nitrogen has a -2 relative to this one having a minus. So 0 is less than +1, so this is better. And -1 is less than -2, so this is better. So this structure minimizes the charge on each of the atoms. And so ultimately, I am going to pick this structure as the best structure because I've, 1, minimized the formal charges on all the atoms, and 2, I've put the negative charge on the most electronegative atom. So I've satisfied both of my rules for figuring out which structure is the best, and I end up with this one being the best structure.